Hare Krishna. Today we're going to see this problem min stack. Basically, it's a medium level problem. However, I feel it should be easy. Let's try to understand this problem statement. Basically, we need to design a stack that supports push, pop, top, and retrieving the minimum element in constant time. So basically, we all know when we talk about stack data structure, so the common basic operations are push, pop, top, right? So push is to insert a new element, pop is to remove and return the top element, and top is just to return the top element. Okay, if our stack is having something, so pop removes and returns this one, whereas top just returns and it doesn't remove. So now we need to focus on one more operation, get min. So the whole challenging part of this problem is how we can develop this particular functionality in such a way it's always going to be big of one time complexity along with these three. But as we know, by default, stack data structure performs these all operations in big of one time complexity only. Hence, I'm not going to focus on these three. Rather, I'm going to focus only on this one, which is specifically too important as part of this problem. So what we are going to do here is, so let's assume we have something like this 0, 2, -3. Let's assume these are three elements. So the end goal is we need to perform this get min operation in big of one time complexity, right? That means constant. So what we are going to do here is we are going to take a stack. Let's assume this we call as a min stack, okay, along with the original stack, okay. So let's try to see how we are going to solve this. So -2, initially -2 will be placed here, and we check is min stack is empty. If min stack is empty, then we are going to insert whatever the first element we got, because this is going to be the min if there is only one element, right? Then we take second one 0. Then we insert 0 here. And we check is 0 less than -2. No, right? 0 is greater than -2. Then out of these two, what is the minimum? -2 only, right? So then we reinsert the same one, -2. Okay? Try to understand, like if 0 is less than -2, then we can insert. But 0 is greater than -2. That means at this stage where there are two elements, for these two elements, the min is going to be -2, right? Let's assume like someone deleted this one, popped up. Okay. Before deleting, they called this get min and we return -2. That's fine. Then they deleted 0. Okay. Okay. Then again they called get min. Then what should be the minimum? Again -2 only, right? Because there is only one element. So that's the reason, like for every element in stack, we are going to maintain what is the min element at that position. Okay. Now we come to -3. -3. Is -3 less than -2? Yes, it's less than -2. So then we are going to insert -3. Now what happens out of these three? Okay, after inserting these three, I mean to say after performing push operation for these three, if someone calls get min, we can see our peak element. That is nothing but our top element is the answer, right? And here we are doing this in big of one time complexity because we just call this min stack dot peak. That's it, which returns me the top element. Now what happens? Someone tries to pop. Okay, now they did this stack dot pop. Then this got removed. Okay, when this got removed, then we are going to remove this one also. All right, because this is no more going to be the minimum. Now there are going to be only two. And someone calls get min. Out of these two, what is the minimum? -2. And we just return again min stack dot peak. Then it returns me again -2. Cool. And someone tries to delete this one also. Okay, then we remove according its corresponding min element. Great. Then there is only one element. And someone calls again get min. Then what is the minimum out of this min stack? Of course, only one element we have. Then we say stack min stack dot peak, then it returns you again -2. Then someone tries to delete this one, then we delete this one also. So basically whenever you try to pop from this, you pop from min stack also, its corresponding, or I can say min element. So that's all this problem statement here. The space complexity is going to be big of n. Okay. Basically where you are going to store the stack and the min stack, big of n plus big of n, to put it in concise way. So the time complexity is going to be the big of 1 for all the operations, push, pop, top, and then get min. So considering the time, so what I'm going to do here is I'm going to retrieve whatever I submitted last time. Okay, I just submitted. So I quickly explain. So I took stack and min stack, two stacks I took, and whenever I'm trying to perform push operation to the original stack, okay, I pushed whatever the value it is. But when it comes to the min stack, if min stack is empty, that means whatever the value which I got, that is the first element, it's absolutely going to be the min. So then I'm pushing here. If that is not the case, if min stack is not empty, then I'm going to check if whatever the value I got, say min stack has already -2 and I got 0. I check if 0 less than -2, no, then I'm not going to do this one. What I'm going to do? Rather, I'm going to take -2, again I'm going to insert that one. But let's assume if I got -3, is -3 less than -2? Yes. Then I'm going to insert -3. So that is what I'm doing here. Then pop is nothing but remove from original, remove from min, and top is nothing but just return from original what is the peak. Min get min is nothing but return the top from min stack. That's it. Let's give a submit. Yeah, it got submitted. It took some 5 milliseconds and 47.66 MB. So that's all for this video. I hope you learned something new today. Till then, Hari Bol.